Hi, kid. Today we are going to learn about another application of derivatives, this one called Newton's method. It's kind of funny historically. Newton's method isn't really from Isaac Newton. Now, the basis of it is Isaac Newton came up with this method for finding, or approximating, I should say, x-intercepts of a function. But it actually was Joseph Rhapson, I think I'm saying his name right. Joseph Rhapson is the formula that you're actually going to use is not Newton's. Again, it's Newton's theory, and Newton came up with a way to do the same thing. Joseph, just as a couple years later, came up with a very, kind of with the same method, but it was a simpler method. So that's actually the formula that we're going to use is not Newton's formula. It's Rhapson's formula. Kind of interesting, right? Newton had done it before, but actually Rhapson was published before Newton. Newton was actually doing a lot of his freaking work during a pandemic, by the way, on calculus. But Joseph was big team Newton, right? There was some debate between whether Newton or Leibniz had come up with calculus, right? Had invented, quote unquote, calculus. And Joseph was big team Newton guy, which I find hilarious that that's what they thought about. But anyway, this is right well before our freaking calculators came into existence. People were approximating, right? And your calculator is just approximating the zero of functions, right? But there was calculators and computers only been around for a little while, so there had to be a way to approximate intercepts that you couldn't find by factoring, right, and solving and stuff prior to the calculator. So again, sometimes we take that calculator for granted and treat it like it's like it has thought, like it can reason or thought. It is just programmed, and it is programmed with this algorithm, and it is just a little bit modified version, but basically this algorithm. So this algorithm, though, does depend on you knowing derivatives, taking the derivative of a function. So I'm going to spend a little bit of time setting this up because in reality, this is a very quick objective. I'm going to give you a formula, show you how to use it. I'm going to show you how to use it if I take your calculator away. I'm going to show you how to use it if I give your calculator. So if you don't have your calculator handy, please go ahead and grab it. So what if I want you to find the positive root of this parabola that opens up? Right, so there's a particular x-intercept that I'm after because after all, this is a parabola that opens up. Its y-intercept is at -3. So it has both a positive and negative x-intercept. And this is a simple equation that I can easily find the exact value of the x-intercept without Newton or Rhapson. But we're going to take something simple and practice the process on it before we get to a more complicated problem. So there's what the graph looks like. And I'm asking you for this root. So the first thing I want you to notice is I looked either from prior knowledge or if I had a calculator in my hand and I didn't recognize the equation, the first thing I did was graph it. What does the graph look like? And I particularly look at the x-axis and say, where about does it cross? And if they're asking me for a positive root, I'm going to approximate. My first approximation is not going to be good. This x-intercept is somewhere between 2 and 3. What if I say, somewhere around 3? That's a terrible approximation. Terrible. But why, if you're going to do a guess and nobody's really judging you, why don't I guess an integer? Right? So that's really the first step to Newton's method is to either be able to look at a picture of a graph or, again, from prerequisite knowledge of what certain graphs may or may not look like, get a reasonable guess of the root or the x-intercept that you're after. Now, I've zoomed in my picture here on the parabola in between 2 and 3. And there's my original function. Here's its derivative, which is just nicely x, right? I'm going to draw the tangent line at my first guess. So remember, I made a terrible guess that this x-intercept is at 3. And it most certainly is not at 3. In reality, at 3, the function isn't 0, it's 1.5. when x is 3, y is 1.5. Right? And I just plugged in 3. Now I've drawn a piece of the tangent line, right? This tangent line really, right? This is an entire tangent line. I have drawn at the point 3, comma 1.5, I drew the tangent line. I stopped the tangent line at the x-axis, and I want you to look at the tangent line's x-intercept. Line, x-intercept. How long have you been finding x-intercepts of lines, right? A line only has one x-intercept. And I want you to notice the position of this x-intercept relative to the actual x-intercept I want. Isn't it closer than my first guess of 3? The x-intercept of the tangent line drawn at my first guess, 3, comma 1.5, is closer to the real x-intercept that I'm after. I'm going to use that knowledge. Notice that the slope of my tangent line is 3. And isn't that actually 3 over 1? And haven't you been since, right, elementary school, talk about slope being rise over run? Right? So I'm going to drop a perpendicular down from the point of tangency. And look at that triangle I have. Now, point 1, point 2. What is the slope between those? Right? Slope between them, rise over run. And remember, run is an x issue. I just called that z. I called that run z because I have too many x's happening already. But I need you to understand that that is, the z is your run, which is an x issue. Rise is a y issue because slope is rise over run, right? So the slope of the tangent line is rise over run, which is 1.5 over run, right? So I'm just filling in the equation. The slope is rise over run. But remember what that run represents. That run is a distance. That is a distance between my first guess and my new guess. That's right, the x-intercept of that tangent line, whose slope I got from the derivative, the x-intercept of that tangent line is going to be my new guess because it's closer to the x-intercept I want. I solved that for z, right? What is my run? Solved that, got run by itself. Run is the y value at your previous guess divided by the derivative value at your previous guess. So notice with my first guess of 3, I plugged 3 into the original and got my run, my rise, my y value. Then I took 3 and plugged it into my derivative to get the slope, the rise over the run. And if I just want run, I am going to divide the rise by the derivative. So guess, plug into the function, get a y height, guess into the derivative, get your run, your rise over your run, solve for the run, use that slope value and rise over run formula or your slope formula to solve for the run. And this is your new, this is the distance between your old guess and your new guess. So what is your new guess then? Your new guess is the old guess minus that distance between your old guess and your new guess. This is your new guess. Woo! So again, took my guess, took my y value from my guess, which is your rise, took the derivative value from your guess, used it. That's how you ended up getting, right? Slope is rise over run. That's how you ended up getting your run value. So the pink box over the tan box is your run, and your old guess minus that distance is your new guess. And guess what you do now? The same thing. Lather, rinse, repeat. Take your new guess, which now becomes your old one. Now, you can call this guess 2 or guess 1. We can kind of consider the guess that you just make by eyeball. We consider that like your 0 guess, if you want, because you're not using the formula to generate the guess. The formula generated this first guess, so I'm going to take that guess, plug it back into the function to get my rise. Take my guess to the derivative rule to get rise over run. Notice that this now becomes the x-intercept of the tangent line is the previous guess. I draw a new tangent line at the point 2.5, comma 0.125. Draw a new tangent line, look at its x-intercept, and look, I'm getting closer to the actual. Just by drawing tangent lines, right? Sliding down this curve, drawing tangent lines and finding x-intercepts of the tangent lines gets me closer and closer to the tangent line of, or the actual x-intercept. Crazy, right? Solve for run. Remember, this is your distance between your previous guess and your new guess. So take your previous guess, subtract the run from your previous guess, and get your new guess. And then once again, what do you do with that? You repeat. And you can, of course, keep going forever and ever and ever. I'm just going to go through one more time. I plugged my guess into the function to get the rise. Plugged my guess into the derivative to get the rise over run. Use the slope formula to solve for the run. The fact that you have rise over run is equal to 2.45, the slope, right? This is 2.45 is the slope. Took the previous guess, subtracted the run to get the new guess. And no, I wouldn't write all those down. If this was my final answer, I would truncate it to 3 places, or sometimes with these problems, because 3 places past the decimal sometimes isn't enough, right? As they ask you to go through, they might say to 6 places past the decimal inside this problem, or they might say till you get accuracy to the 6th place or something, which just means you have to go far enough to show that you repeat whatever. If they said 1, 2, 3, 4, 5 to the fifth place past the decimal, I would have to run the algorithm until this 5th digit repeated twice. So I stopped Newton's method there, and then I checked my work by taking this now. So I didn't write all this down. I stored this value, and then I plugged it into Y1, and I didn't get exactly 0, but I got pretty freaking close to 0. So this is a very good estimate of the x-intercept. So again, your calculator is programmed with this method. It just can't actually find the derivative because it can't do calculus. So it approximates the derivative value as well. But that is Newton's method. It is called recursive because each step depends upon the previous step. And sometimes you might see language in the problem saying how many iterations you need to go through. Iteration is just a synonym for step. How many times did you go through? And again, recursive just means that you can't just jump to the end of Newton's method. You have to have the previous answer. So let me show you an example of, I just did that example without the calculator. My next one we're going to do with the calculator. But you do want to write in your notes that Newton's method, right? And really Newton gets the name just because he came up with the theory of it first. Then the proof, I guess. Guess, because step 1 is guess. And remember, you're guessing. Sometimes what AP will do so that everybody starts from the same place is they will give you the first guess. They'll say like x sub 0 is 1 or whatever, right? AP will often do that. Or you're looking at a picture of a graph, right? Either on your calculator or they've given you a picture of where y is equal to 0. That's an x-intercept, right? Of the x-intercept they want. So you're going to use the 0 guess to get the second to go on the third, using this formula. So this formula is worth writing down, but it's also worth writing down the English that goes with it. The next guess of the x-intercept is, that's what an equal sign says, is the previous guess minus a ratio So even if you don't remember that is that's the run, that's the z, you can memorize the formula as previous guess minus fraction, and the fraction is plug the previous guess into the original, plug the previous guess into the derivative, and divide. Okay, that is actually Rhapson's formula, right? Newton's was a lot more flowery and a lot more verbiage and proofy and all that. And here's what thanks Joseph for just giving us a formula. So here's a nice little applet that shows an x-intercept over here. And look at the successive tangent lines getting closer, x-intercepts of the tangent line getting closer and closer. And it'll repeat itself if you missed. Right? First guess is way over here. That's a terrible guess. Tangent line gets me all the way here. Second guess, draw a tangent line. X-intercept is now on the left, but it's closer. Draw a tangent line there, right? So can you see, though, that the point, even though I bounce back and forth of the x-intercept because of this function behavior, still the distance from my new guess to the actual intercept gets less and less. So let's look at this one. This at first doesn't look like I should use Newton's method on it, because this is asking me, where does x cubed minus x equal 1? Newton's method is for finding x-intercepts. Well, I think you can do algebra 1 on that, can't you? In pre-algebra. Now I can use Newton's method. Right? Newton's method does require that you are looking for x-intercepts. So you do have to be equal to 0. So that's what I did first. And then I found the derivative. So this step here was only necessary because they didn't give me just f of x, right? But I turned it into that by making this equal to 0. Then I found the derivative. And now I'm going to make a table. You do not have to make a table like this, but AP recognizes this as Newton's method work, and so do we. So some students just like to run through the steps like I gave you in the previous problem. Some kids like to organize with a table. So notice that the columns of my table list my previous guess evaluated in the original, my previous guess evaluated or plugged into the derivative, and then here's my formula. N is the number of iterations. So really, as I said, the 0 iteration is when you're not using the formula. So you're just using it from a graph. So I'm going to give that to you. I'm going to give you your first guess is 1. So first, plug 1 into the function. 1 cubed minus 1 minus 1. Then plug your first guess into the derivative. 3 times 1 squared minus 3. Now do 1 minus negative 1 divided by 2. One minus negative 1 divided by 2, which is 1.5, which is your next or your new guess. I got that guess using the formula, so I call that 1. I don't care about this column. I don't care if you start this at 1. Sometimes the question will say, how many iterations does it take? If you started this at 1 and I started at 0, so my answer is 4 iterations and yours is 5, I don't care. I need to see your work, okay? I need, whether it's in just setup form, going through each equation, like the first example I did, or whether it's in table form, I don't care, right? And AP doesn't either, I promise. All right, so forget about the fact, right? Forget about this column, really. Sometimes this column is more confusing than it needs to be. My next guess is 1.5. So I'm going to plug 1.5 into the original, and I get 0.875. I'm going to plug 1.5 into the derivative, and I get 5.75. And then I'm going to do 1.5 minus this ratio. And I do carry my decimals while I'm inside the work. I carry all these. Now, I don't actually write them down. but I store them using, because with these numbers, you would have a calculator with these numbers. My next guess is all of that, not that approximated, all of it, 1.34782661. Plug that value into the original, plug that value into the derivative, did my ratio. And I'm done. So this problem might say something like, run through 2 iterations of Newton's method. That does mean use the formula twice, right? With a guess. So I guess you're technically using it 3 times. Again, when in doubt, do one more. I took this number, I stored this in alpha B. Because I'd stored this in alpha A. And then I plugged this into x cubed. X cubed, right? So I did alpha B cubed minus alpha B, and I got not 1, but I got something pretty close to 1. Okay. So let me show you a neat little thing you can do with your calculator to speed this up. So of course you can just plug the equation into y1 and look and use second trace intersect. But if you are prompted to use the Newton-Rhapson method or just Newton's method, they are going to expect to see some work, and I'll show you what they expect to see. Firstly, they could put the question on a non-calculator portion, of which case they're only going to ask you a few steps, and they're going to make the numbers, they might have fractions in them, but the numbers will be not like that last example with all those decimal places. But even if you have a calculator and they ask you to use Newton's method, you cannot just find the x-intercept. Any other time you have a calculator in your hand and you need an x-intercept, you don't have to use Newton's method. You just do second trace intersect, right? Or second trace 0. But if they ask you for Newton's method, you must show you are using the formula. So I'm going to do that same problem, and I'm going to show you some keystrokes that I use on my calculator, right? So I put this into y1 and I looked at it. And remember, they gave me my first guess as 1. But even if they hadn't, I would have guessed either 1 or 2. And it wouldn't matter which one I did, right? If they don't tell you which guess to start with, then they give you you're either looking at the graph on your calculator or so they gave you a picture of a graph, and you better pick either 1 or 2 to start with. So this is what I actually do. This is not what I write down for credit when they ask me to do Newton's method. So I firstly, of course, got it into Newton's form by putting it equal to 0, right? And then replacing it with either f of x or y. I did put this into y1. So you take a moment and do that, please, if you haven't already. Put the original equation into y1. If they didn't give you a first guess, use the graph to guess and guess an integer. Be nice to yourself. Now, on your calculator, on your home screen, type 1 and then type the arrow. You get the arrow from the stow button, stow for store, and it is to the left of 1 and a little bit above, to the left of the button 1 and a little bit above. Store that in x, and it doesn't matter whether you use the variable x, right? Like just when you're typing x cubed, you can use that, or you can use alpha x. It's the same cell in the calculator's guts. We usually tell you never to store something in alpha x or alpha y for that matter, because Your calculator is programmed to populate that cell, the X cell and the Y cell, with X and Y coordinates from a graph. And of course, if you've reset your computer, the X and Y coordinates would just be 0, 0. But as soon as you put a graph in there and move your cursor around, the X and Y coordinate of the last place your calculator stopped, your cursor stopped, those values are populated into the X and Y cell of your calculator. So that's why we tell you never to store something in there, because it gets rewritten over anytime you access your graph. So, but this time I am telling you to store your first guess. Now I want you to put the derivative into y2. You can either, this derivative is easy to do, 3x squared minus 1, or you can just do math 8. The actual derivative, or you do math 8 with the function that's in y1. Then you go back to your home screen and type this sequence. Hopefully, again, you know how to access y1 and y2. That's the button vars, arrow over to y vars, hit 1 for function, and then you should see y1, y2, y3, y blah, 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 blah. Notice that you don't have to have any parentheses here. By default, when you hit y1 enter, the calculator will automatically use the X value that is stored in its X cell. It will only plug in a different number if you tell it to, but we don't need it to. Notice that don't hit enter. Don't hit enter after you have y2. Hit store again and store in alpha X and hit enter. Whoa. Now hit enter again. It's a loop. It's a loop. So let me go and show, just in case this wasn't working for you. Oh, wait, I'll go back to the calculator, but before I go to the calculator, I want to show you what I would have written down. Oh, crap, where's already trying to go to my calculator? Oh, there we go. So this is, if I have my calculator, this is some stuff that I would have done, but that's not what I would write down for credit. What I would write down for credit is the derivative. If I don't have my calculator. If I have my calculator, I'm just going to say y prime. I'm going to tell them what I started with if they didn't give it to me, right? Sometimes this is given. If it's not given, I'll tell them where I started, because maybe I would have started, maybe my first guess would have been 2, right? Which is also reasonable. Then I would write the formula down. So tell me what your derivative is. Tell me where you started, unless it was given. If it was given to you, I don't have to see this step. Then show me the formula run through. I only, with you, you have a calculator in your hand. Right? I don't really even need you to write the derivative down since you have a calculator in your hand. That's really for the non-calculator portion, because you're going to have to see the it's in your best interest, if you don't have a calculator, for you to write the derivative down so I can see what you're plugging into. But I really just need this. And I only need it one time, that you got 1.5. And then after that, I just need to give you however many iterations I asked for. Okay? I don't need to see you write it out multiple times. Again, you can use usually the table is if you don't have a calculator, and it's for you to be able to keep track of what you have. But if you've got a calculator in your hand, write this stuff down, right? This is all your point value is going to come here. Probably +2 for this setup and answer. And then there's going to be 1 point for the answer, right? However far I asked you to go. Now, warning before I'll demonstrate my calculator. Sometimes Newton method doesn't work. Every once in a while, if you're not careful, if you're looking for like the left root, but your initial guess is past this vertex and you guess over here, it's going to search for the wrong root, right? Let's say you guessed over there. It's going to go for the x-intercept on the right. If your derivative is not defined, it won't converge to the x-intercept. You'll go actually farther and farther away from the x-intercept if you have some issues. All right, let me go to my calculator. So I'm going to put the function in y1. Oh. And the derivative in here. And of course I know the derivative, but vars, y vars, enter y1 for all x. I want the calculator to have the derivative of the function I put in y1 for every x. Quit to my home screen, and I'm going to type 1 store x. And again, you can do alpha x or variable x. It doesn't matter. So it is now stored in there. Then I'm going to type my first guess, which was x, minus the ratio of the first guess plugged into the original function divided by the first guess plugged into the derivative. And I'm going to store that answer in x. Now, I don't get 1.5 because I didn't type in the exact derivative. It's fine. It's close enough. But notice what happens when I hit enter again. Oh my gosh. Right? Hey, I'm starting to, can you see the decimals, right? Look, I went through it these 2 times and the decimals repeat. Let's look at the graph of not the derivative. Turn it off. If I look at the graph of the original, and I use the calculator, to find the x-intercept, whoops. Look at that guess, right? That really is the calculator's guess, 1.324718. 1.324718, right? See what I'm saying? Newton's method. Pretty cool. Thanks, Isaac. Thanks, Joseph. You guys are great. All right. I will see you in our next live session.